your Spotify recommendations, Instagram feed, YouTube algorithm, ChatGPT. Completely different technologies, yet deep underneath, all of them rely on the same tiny mathematical building block, the neuron. A neuron takes inputs, multiplies them by weights, adds a bias, applies an activation function, and produces an output. And this entire process can be summarized using one equation. Simple equation, revolutionary impact. This tiny idea became the foundation of modern deep learning. Everything starts here. Now let's zoom into the first step, the weighted sum. A neuron receives multiple inputs, but not all inputs matter equally. That's why every input gets assigned a weight. The neuron multiplies every input by its corresponding weight, then adds everything together, along with a bias, mathematically following the formula of pre-activation, which is given here. Or more compactly, in the vector form, it looks like this. The weights control influence, while the bias shifts the neuron's behavior. This weighted sum, called Z, is the neuron's raw score before activation. Simple math, but massive impact. But here's the problem. Without activation functions, neural networks are basically just linear equations. No complexity, no intelligence, no deep learning. Activation functions solve this by introducing nonlinearity. Let's start with sigmoid, which looks like this. Sigmoid compresses values between 0 and 1, making it useful for probabilities. But deep networks often prefer ReLU, which is rectified linear unit, and for it, the formula looks like this. If Z is or the Z is positive, keep it. If it's negative, output is 0. Simple, fast, and incredibly effective. That's why ReLU became the default activation in model neural networks. Now let's connect everything together. Input enters the neuron. Each feature gets multiplied by its learned weight. The weighted sum is computed, bias is added, and finally, the activation function transforms the result into the final output. The process starts here with the equation z equal to w times x plus b. Then activation is applied. For sigmoid, it is y hat equals to 1 upon 1 plus e to the power negative z, and for ReLU it is y hat equals max of 0 and z, and that final output becomes the input for the next neuron. That's how deep neural networks are formed. Now let's begin with the implementation of a single neuron. Here we will be implementing the function forward in the solution class. As we have seen before, a neuron takes a vector of inputs x and multiplies each by a corresponding weight w, adds a bias b, and passes the result through an activation function, which looks like this. So we are going to implement this here. We are given with a forward function which takes parameters self and x, which is the array of features, w, which is the array of weights, b bias, and activation function. Let's start. Let's first calculate z. So z would be calculated using the formula which is also given here. So z equals to the dot product of x and w plus bias. And after that, we will be using conditional statements. So if activation equals to sigmoid. So if activation equals to sigmoid, result equals to 1 upon 1 plus np dot exp negative c. So this is the formula for our sigmoid activation function, and then we are going to use another conditional statement if activation equals to ReLU. Result equals to NP dot maximum of 0 or Z, else result equals to Z, and then we'll just return result rounded to 5 decimal places. So result which will be rounded to 5 decimal places. Let's test it. Yeah, so a single test case has passed. Let's submit it and see. And yes, this is how our implementation is done. And that's the complete neuron. One formula, one forward pass, and one output. Yet this tiny mathematical unit powers the entire world of deep learning. Every neural network, every transformer, every large language model is built from millions or billions of these neurons connected together. At the center of everything is this equation. But here's the real question. How does a neural network actually learn the correct weights? How does it reduce mistakes over time? That's where the real magic begins. Backpropagation. In the next video, we'll break In the next video, we'll break down how neural networks learn using gradients, chain rule, and gradient descent, visually and step by step. So if you enjoyed this breakdown, make sure to like the video, subscribe to the channel, and I'll see you in the next one.